guys. Wow. I am excited to be here. I hope you guys are doing okay. Who's out there? Hi, how are you? How are you? Good? Good, going okay? Ian, how you doing? Good. My name is Tom Petersen. I have two IPs to introduce you today, a GPU and an NPU, and we're really excited about both of them. But they come about like, why do we need to keep investing in these IPs? And obviously it's because things keep changing, right? We're moving forward in technologies. We're getting new devices all the time, new form factors, maybe a little bit more mobile, maybe a little bit larger panel, maybe a different kind of use case. But these devices are changing all the time, and workloads are changing all the time. Everybody knows that AI is the thing, and agentic workloads have dramatically changed the requirements for PCs. And that means that we have to continue innovating on the IP side. So that's what you're going to see today, is a bunch of new innovation that's in response to the changing environment around us. So we have a GPU to talk about and an NPU to talk about. The GPU is primarily modified to support much larger configurations. I'll show you today that Intel has made the largest investment in GPU IP and in GPU area that we've ever made for an integrated graphics device. And that's pretty cool, because we can do great things with it for our users. And also on the NPU side, you'll see that we have embraced agentic AI. And the NPU is growing in capabilities and efficiencies so that we can bring that down across our entire stack. High-performance NPUs have sort of been constrained to the upper part of our stack. With Lunar Lake, they're coming all the way down. And that requires optimizations and efficiencies. Okay, so let's dive into the GPU IP. And I mentioned it's got two primarily things that we focused on: building larger configurations and improving the throughput. So on the larger configurations, let's start with a recap of Xe2. As you know, this was introduced with Lunar Lake. And in this design, we really redid our Xe core, which is sort of our fundamental compute block. We added XMX engines, which are effectively large structures for matrix multiplication to accelerate AI. We really doubled up on our ray tracing units. And overall, I would say the engine itself really uplifted graphics at Intel. This is also the same engine that we integrated into Battlemage, our discrete GPU, and we went on to have some fairly significant success with that device. Moving forward, we are going to be moving the product family up. You can see here it's kind of like a decoder, because this has been a little complex for people to understand. On the top is the name of our architectures. So you'll see Xe and Xe2. Those are our major architectural families. I'm trying to simplify a little bit, because we went a little crazy with names. Then down below are products that we've launched with different IPs. So Alchemist, our first discrete GPU, and then multiple different integrated SoCs, all called Intel Arc Graphics, was the name of the GPU inside those guys. Then with Xe2, we launched with Lunar Lake, and we called the graphics chip inside of it Intel Arc Graphics. But eventually, we launched Battlemage, and Battlemage became well known for its branding, the Intel Arc B series. And so we've decided to go ahead and carry that name along as we introduce our new architecture, Xe3. Xe3 will first launch with Panther Lake, and you'll see that we're actually going to use the Intel Arc B series name again. So even though it's an Xe3 architecture, the product name, the GPU inside of Panther Lake, is going to be branded B series. So it's a little confusing, but you get the idea. The brands are going to be moving at a separate cadence from the IPs, etc. Following Xe3, there will be an Xe3P. And Xe3P is, again, a significant step forward in graphics IP that will be launching in a next yet-to-be-named product that I'm not going to talk about at all today, so relax. Okay, so let's dig into a little bit of what makes Xe3 so cool, because it is very, very cool. And the first thing we've done is dramatically increase the scalability. And the way we do that is by increasing our sort of infrastructure. You can look at the block of Xe2. This is the render slice. And the render slice is sort of the fundamental modular building block of our IP. It's got inside of it our Xe cores. And the Xe core is sort of our sub-block, which is the compute block. And you can see our ray tracing units and the rest of the pixel backend. On Xe3, we're actually increasing the size of this thing. So we go up to 6 Xe cores per render slice from 4 to 6. And we're scaling out all the resources required to make this bigger, sort of fundamental building block of our IP. The Panther Lake die is going to have 2 different variants. There'll be a 4 Xe GPU die, or device, and a 12 Xe GPU device. And so you can see with the 12 Xe GPU device, it's the biggest, most performant GPU we've ever built for integrated. Looking at the numbers, the Xe3 4, which is the 4 Xe configuration, has 4 Xe cores, 32 XMX engines, 4 megabytes of L2, et cetera, et cetera. It is basically a very performant GPU. When you compare it to our 12 configuration GPU, you can see things just scale up. 12 Xe cores, 96 XMX engines, 16 megabytes of L2, and 2 geometry pipelines in the back. Overall, it's going to be great performance, but I think the key thing is to dig into what's different. Well, the first thing we've done is increase the size of our L2. L2 is sort of like a chunk of storage on die that captures memory traffic that misses in our L1s. So you can see by increasing the size of the L2 from 8 gigabytes to 16 gigabytes, 8 megabytes to 16 megabytes, we reduce the traffic that hits the memory interface. That's important because memory interface is typically one of the most precious resources on a graphics chip. So we can see anywhere between 17% and 36% traffic reduction heading towards memory, which has a significant performance effect on these different applications you can see ranging from 3D Mark to Black Myth Wukong. Now let's talk about performance optimizations, because there's a lot of work that happens here. Every generation, our engineers spend countless hours looking at traces, looking at games, looking at compute, trying to figure out how can we improve things. And really, every generation, we've made significant steps forward in optimization and I almost say like utilization. When we first launched Arc, I did a whole conversation with some of our guys about how utilization is underutilized. We had work to do to take advantage of all these transistors. We're almost where we need to be, so it's dramatically improved. And you can look at it in 3 main blocks here. We've got our 3rd gen Xe core. I'll talk a little bit about the technologies there. We have a new improvement to our Xe vector engine, which is sort of our compute block within the Xe core. We have enhanced our graphics backend fix function. I'll walk you through that. And we've improved our ray tracing unit. So it's like the 4 fundamental blocks that make up our render slice. Looking at the Xe core, we have 8 512-bit vector engines, 8 2048-bit XMX engines, and we've increased the size of the L1 by 33%. So that all results, that's 192 kilobytes up to 256 kilobytes. So we've on the Xe vector engine, we've increased utilization. We're up to 25% more threads, variable register allocation, which is huge. Effectively, one of the most precious resources inside a GPU is the registers. They're expensive. They have lots of wires connected to them. So utilizing those efficiently per thread is critical. And we've actually re-architected how we manage these threads completely and gone to a variable allocation strategy. You'll see this has dramatic effects on performance, but it's one of the key things we've improved. We also support FP8 dequantization support, which is critical for different data types moving through the pipeline. You can expand it or contract it as needed. We've improved from a max of 8 to 10 threads. All right, on the XMX, we're up to 120 TOPS. So this is the primary engine that runs high-performance AI on Panther Lake. When you're thinking about AI, you should be thinking about matrix multiplies, and matrix multiplies are what XMX does. It does 1024 TF32, it does 2048 BF16 and FP16, and we do 4096 int8. And so that's really a cool thing. I'll go into it this afternoon about how quantization works. But the idea is that you get these very complex, big models, 8 gigabyte models, 8 gigabyte parameter models, and you're looking for ways to run that on a local GPU. Well, what you do is called quantization. And quantization shrinks the size of the weights, it shrinks the size of the activations, and runs it with like more sort of primitive mathematics. And that's really what XMX has been optimized for. Okay, so Our enhanced ray tracing unit is all about improvements to the way we allow rays to flow through the pipeline. So in this case, we slow down dispatch of new rays while sorting unit catches up. So we got this thing that's sort of an out of order, you dispatch lots of rays, you're testing lots of triangles, and then effectively you have to resolve those in order, and that's what our thread sorting unit does, but that can cause backups in the pipeline. So we've re-architected that, and now we can actually slow down our dispatch to prevent lots of queued up rays for resolution. That's what dynamic resolution of rays is there. We also now have a new URB manager, which allows partial updates versus flushing the whole thing. So our URB is a structure where we pass results between our units inside of our GPU. And it used to be somewhat of a serializing point. Now we can actually use that partially without flushing from each context. It's a very nice improvement. We support up to 2x the anisotropic filtering on die. Anisotropic filtering is a form of texture filtering. I've been saying it wrong for 20 years. I used to say like anxiotropic because I have dyslexia. So this weekend I learned anisotropic. Very exciting. All right, so that summarizes a lot of the things we've done with Xe3. It is a brand new IP. It's optimized from our engine to our slices, and it scales dramatically larger and more efficiently because we've increased resources and improved efficiency. So let's look at what you get with this. And the way to understand it easily is to look at micro benchmarks. Micro benchmarks are effectively an engineering application. We write them ourselves. They're sort of little tiny kernels. And you're trying to test out specific microarchitectural features. In this case, I'm showing you between Xe2 and Xe3, there's been really no change for the blend or for the backend, and that's because the resources dedicated to that is unchanged. If you look at our render slice, it has a common geometry backend that has not changed. If you look at GEM or FP16 or FP32, these are basically scaling up by 1.5x. Because these are optimized micro benchmarks, they're fully utilizing our registers, they're fully utilizing our compute, and they're going to scale by exactly the size of our Xe core ratio in the render slice. So we've improved our renders, like our Xe core to render slice ratio by 1.5x, and that's why it scales. The next collection of things are microarchitectural improvements. We've improved our ray transfer rate by 2x, our aniso filtering by 2x, mesh rendering by 2.4x, and scattered rees by 2.7x. These are all related to microarchitectural improvements inside of the Xe core. Lastly, some things got a lot better. So you can see up to 7x for depth testing, depth writes. You can see up to 3x faster for register-heavy applications. This is where the variable allocation plays a key role. So you see all these different results across multiple different benchmarks are the result of lots of work by a ton of engineers. All right, now let's think about how this core affects Panther Lake, right? Because that's really what we care about. At the end of the day, you can see this curve on the top, which is purple. That is the new Xe3 Panther Lake. It's more performant and less power, which is a rare combo, right? We haven't really changed process on this device. So you can see we are 50% more performance. If you look at our peak power, 50% more performance. That's coming from all the things we've talked about. It's got a bit that comes from more area. It's got a bit that comes from a little bit more power. And it's got a bit that comes from higher IPC per core. The second way to think about it is that we can run 40% higher performance per watt. So this says we're just being more efficient, right? We are a wider configuration. At the same power, we can deliver more performance. But it's not just about IP. Obviously, we're constantly working on our software stack. It's near and dear to my heart. This is an easy way to think about it, right? At the bottom is our GPU, and in the middle is our entire stack of drivers and firmware. So there's GPU firmware running on the cards. There's a KMD driver and a UMD driver. And then on top of that are third-party things, and some of them are eyes. Our stuff is like XeSS and the BPL runtime for media. So our stack is really from the bottom all the way to the top, millions and millions and millions of lines of code. But we've made some key improvements. First of all, IGC, which is our compiler, Everything we do on the GPU has to be compiled because it starts from effectively vector or vendor-neutral source, and we compile it through IGC down to our target. And we've improved IGC for variable register allocation, which is key. We also now support faster scheduling with direct preemption. That means that we can swap between contexts without flushing, which is cool. And we support DirectX cooperative vectors. This is critical. I don't know if you guys have really heard about it. It launched a little bit earlier this year. We've been working very, very closely with Microsoft on this. But cooperative vectors is a standardized way to support multi-vendor code bases. You can actually code for matrix operations and vector operations inside of shaders. So you can more closely couple AI algorithms to your fundamental render pipelines. So this is going to make it much, much easier for people to incorporate AI in, for example, games. So this is a first example of what you can do with cooperative vectors. So it's a little bit complicated, but as most of you guys know, when you're doing graphics, you start with a three-dimensional model. Some artist creates it, it might be a Nerf figure, and that model is just perfected, almost like a sculpture. It's very expensive. At the same time, they create textures, or they do photogrammetry. So it's like this model is just beautifully handmade by a human. And that's why game art is such a significant component of expense. So what a bright person thought of is, what if in the future I have graphics that don't have geometry? And it's a hard thing to think about. How do you do rendering with no geometry, with no textures? And the idea is I'm going to replace that entire render pipeline, that raster process, with an AI model. And the idea is, on the left here, over here, you see this like 3D guy. And I'm showing you two pictures. Well, the idea is that you don't have a model, you just have these pictures. And we're going to train an AI so that if I shoot a ray into this space, the AI will tell me a color. So that's what I'm telling you in the middle. On the left edge, we're saying there's a position in the volume, and there's an angle of a ray that's going to go into that volume. And on the right side, I'm going to tell you that the model is going to spit out just a color and effectively an alpha, which is a transparency factor. So effectively, we can completely eliminate the render pipeline and replace it with a per-pixel AI. So to regenerate an image, you just shoot the rays from the screen, right? You're kind of thinking, 1920 by 1080. Shoot that many rays, and you will get that many colors, and that's your render pipeline. Is that clear so far? OK, so I want to show you this live. So let's get ready to pull up the demo. And this is running in real time. This is a guy we call Nerf. And what's interesting about it is there's no geometry here. This is running AI on Panther Lake. In the back, it's one of the reference designs. And it's running at about 40 frames a second. And you can actually zoom in and scroll around, and you can see this might be kind of a look forward into a future where graphics is really substantially different, and it is primarily AI. It's pretty cool. And that's because of cooperative vectors. All right, let's come back to the slides. We'll put that, I think that's going to be out in the experience room if you're going to play with it and kind of look around it and check it out. It's pretty darn cool. OK, this used the hardware ray tracing to interrogate the design, and it does about 100 inferences per pixel. So if you think about it, that image you were looking at, the amount of inferences that's happening per second is only possible because of the Panther Lake XMX design. So Panther Lake Xe3, let's summarize it, right? It is 12 enhanced ray tracing units, 12 third-gen Xe cores, 50% faster graphics, 50% better efficient graphics, perf per watt, 40% perf per watt. And of course, I didn't mention it, but we have next generation media and display integrated as well. And altogether, it's a big step forward for graphics and for Intel graphics specifically. Pretty excited about it. All right, moving on. The second IP is our brand new NPU. And as I mentioned, we are focusing on bringing that down the stack consistency across our stack. So we had to do some stuff to make that cost effective. And of course, we're continuing to optimize performance on the NPU. So this is where we were with Lunar Lake. This is NPU4. It had 12 shaved DSPs. If you think about the fundamental architecture of this device, there's a DSP, which is sort of our exception path. It does anything that we don't have hardware for. And then there's our neural compute engine, which is dedicated hardware that just does inference. And so that means that it knows about things like activation functions, and it knows about matrix multiplication, and it's very much an inference engine, and anything that doesn't fit because there's standards changing runs on the shave. Okay? So this is where we were with NPU4. We had an efficient, optimized MAC, lots of activation programmability, but we had work to do to optimize the cost. So that's where we focused on NPU5, is bringing it down and working on area efficiency. The biggest thing we've done is re-architected the way the MAC works. The bulk of the NPU is a MAC array. And a MAC array is a collection of cells that primarily do multiplication, right? They're doing very large matrix multiplication, and then they're passing the results sort of down the stack to their neighbors. They're accumulating these very wide, very parallel multiplications. Now, before, on the left-hand side, which I think would be here, you can see how we have 2 MAC arrays per slice, 2 neural compute engines, 4 shaved DSPs, and 2 copies of the backend, right? Now, that's actually pretty inefficient because what we really want is more MACs and less of the other stuff. So in the next generation, NPU5, we've doubled up the size of the MACs per neural compute engine and kept all of the overhead roughly the same. So we have 2 shaved DSPs and 1 copy each of the backend. So think of it as we're getting a lot more MACs per unit area, which results in a lot higher performance per unit area. This is a look at Lunar Lake compared to Panther Lake. NPU4 on the left, NPU5 on the right. NPU4 had 6 neural compute engines. NPU5 has 3 neural compute engines, but they're twice as fat. They're basically twice as many MACs per neural compute engine. Digging into this, you can see there are 3 neural compute engines, which I told you is our sort of our inference engine. We have 12 MACs, 4.5 megabytes of cache, 6 shaved DSPs, and 256 kilobytes of L2. And so this is NPU5, and the key thing it does is drives performance forward and shrinks area down so that we can put it all the way down our stack. It's 40% better TOPS per unit area. And that's, again, coming primarily from the fact that we are doubling up the MAC. It's also going to be optimized. So we haven't just done sort of configuration re-architecture. We continue to work on the low-level pipelines. And you can see, some of the first things we've done is we've improved the way our math works. Previous IP required padding. And the padding actually says, as you're putting math into your these structures here, these MAC multipliers, you normally couldn't slice it up and have different threads running on different bands of this thing. You had to pad it out with zeros. Well, that's been fixed, so now we're seeing much higher occupancy of our multiply accumulate array as data moves through. We can actually do a bunch of multiplies in parallel. We have 4096 MACs per cycle, 4096 8-bit MACs, and 2048 16-bit MACs. So this is just a massively wide, deep multiplier. What we've added as well is support for FP8. So we talked a little bit earlier about quantization and how important that is for running AI on local networks. In this case, we just added FP8. We used to be FP16. And so effectively, when you don't need that granularity, when you don't need 16 bits of mantissa, you can actually double up your throughput through the engines. And that's really what happens. You see much faster, much lower memory footprint, and much higher execution bandwidth. If I show you an example of what this looks like, on the bottom is the result with FP8. On the top is FP16. And I'm showing you effectively the utilization of the NPU and the CPU. So this is running stable diffusion. And you can see we're really, really spiky because we're doing multiple paths of stable diffusion. And that's all 16-bit math on the top. But the truth is, for stable diffusion, you really don't need, most of the time, 16 bits. So we can get the same quality results running 8 bits. And in that case, our GPU is basically not used until the end for blending. Our NPU is used at a lower power level, and it's used for a shorter period of time reducing the energy from, about, let's say, 100 down to about 70, which is about 50% reduction in power or perf per watt. So MP8 is a very nice enhancement for our GPU. Another problem we have is that we're dealing with multiple different levels of quantization in the networks that we're running. So one layer might be FP32, another layer might be FP8, another layer might be integer. And the key thing that has to happen is you have to convert the results across these different computational stages. That's what this data conversion guy does. He converts from effectively any format, almost, to any other format. And what we've done is converted from a custom internal database or an internal structure to standardized FP32 as our normal computational data. And so now we actually store intermediate results in either FP32, FP16, BF16, and so forth. This allows other IPs to read the partial results of the NPU. Pretty cool. Another big innovation is a programmable activation function. So we used to have effectively a somewhat linear activation function support. Now we are actually supporting a wide programmable activation. So you can kind of get things like sigmoids, you can do tangents. We still obviously support our piecewise linear, but now having this programmable things means we don't have to punt as much processing to the shaved DSP. Because before we had support for sigmoid, as an example, one of the more popular activation functions, all of this processing would be emulated on a DSP. So all of that goes away, and it all moves to directly into the neural compute engine. And it's done with a lookup table that is 256 steps. So imagine that little sigmoid chopped into little chunks. You get very accurate behavior. All right, so what did we get with our brand new NPU5? This is the same idea. This is micro benchmarks that our teams run. And you can see when we're running int8 or FP16, we get small boosts. That's like little microarchitectural things we've done. We don't go down. Even though the NPU is actually significantly smaller, the performance stays the same or actually goes up. Now, when we get to things like softmax, that is running on the shaved DSP. And you can see that we have slightly lower shaved DSP performance per core, effectively. So it goes down just a little bit. But when we use our programmable lookup table, which is our activation functions, that moves processing from the shaved DSP onto the neural compute engine, and performance goes way up. So you can see these micro benchmarks are kind of giving you a sense that even though it's been an area-optimized design, the performance is still staying the same or going up. The last two cases I'm showing you are padding and the, excuse me, the FP8 that I talked about. All right. So let's summarize NPU5. It is 40% faster tops per area, which is pretty spectacular, and it delivers up to 50 tops. So when you start thinking about this afternoon, I'll go through what agentic AI means for PCs. I hope you come because it's pretty cool. That agentic AI is relying on engines like the GPU and the NPU, and as we improve our tops behavior and reduce our size, it's going to become standard across our product. We have 3 AI engines in Panther Lake. We have the CPU Stephen talked about, 10 tops. We have the NPU up to 50 tops, and the GPU up to 100 tops. Stephen wants me to tell you these don't really add up, but it's still a big number, and I'm pretty excited about it. It gets you a sense, you're going to be using these different engines in different applications. The CPU is great for light AI workloads, things that are integrated very closely either to an application or the OS. The NPU is great for always-on kind of things, very low power, sort of always doing things. Copilot Plus is going to be great on the NPU. And the GPU is more for dedicated workloads that are more compute intensive. So things like large LLMs or maybe doing some kind of generative AI. So it's a strategy that says the workloads on the GPU and the NPU and the CPU balance out to deliver this new kind of AI-infused PC. So with that, I'm going to introduce Tom Ryder to talk about our IPU, and thank you very much. I'll see you guys later.